Google.
The average person over their lifetime is exposed to about 100 million words of conversation. And so if you multiply that by the 6 billion people on the planet, that amount of words is about equal to the number of words that Google has available at any one instant in time.
Google's computers hoover up and file away every document, web page and image they can find. They then hunt for patterns and correlations in all this data, doing statistics on a massive scale. And for me, Google has one project that's particularly exciting: statistical language translation.
We wanted to provide access to all the web's information, no matter what language you spoke. There's just so much information on the internet, you couldn't hope to translate it all by hand into every possible language. We figured we'd have to be able to do machine translation.
In the past, programmers tried to teach their computers to see each language as a set of grammatical rules, much like the way languages are taught at school. But this didn't work, because no set of rules could capture a language in all its subtlety and ambiguity.
Having eaten our lunch, the coach departed. Well, that's obviously incorrect. Written like that, it would imply that the coach has eaten the lunch. It would be far better to say, having eaten our lunch, we departed in the coach.
Those rules are helpful, and they are useful most of the time, but they don't turn out to be true all the time. And the insight of using statistical machine translation is saying, well, if you got to have all these exceptions anyways, maybe you can get by without having any of the rules. Maybe you can treat everything as an exception, and that's essentially what we've done.
What the computer is doing when he's learning how to translate is to learn correlations between words and correlations between phrases. So we feed the system very large amounts of data, and then the system is seeing that a certain word or a certain phrase correlates very often to the other language.
Google's website currently offers translation between any of 57 different languages. It does this purely statistically, having correlated a huge collection of multilingual texts.
The people that built the system don't need to know Chinese in order to build a Chinese to English system. They don't need to know Arabic. But the expertise that's needed is basically knowledge of statistics, knowledge of computer science, knowledge of infrastructure to build those very large computational systems that we are building for doing that. Okay, so then I'm going to invite...
I hooked up with Google from my office in Stockholm to try the translator for myself.
I will type some Swedish sentences.
Okay.
Sveriges
Guldring I örat.
Okay, so it says Sweden's finance minister has a ponytail and a gold ring in your ear. So I guess it probably means in his ear.
Correct. It's amazing. He comes from the Conservative Party. That's the kind of Sweden we have today. I will type one more sentence. I sitt samköna partnerskap,
nya biskop.
In his same-sex partnerships has Stockholm's new bishop and his partners a 3-year son. That's
It's almost perfect.
unusual.
At least one important thing, it's her. It's a lesbian partnership.
Okay, so that's those kinds of words, his and her, are one of the challenges in translation to get really those right
And
in
especially
MT.
when it comes to
Bishops, one can excuse it.
Right. So that, I guess more often than not it would probably be a his.
I will write one more sentence.
När Sverige deltar i olympiader är målet
Inte att vinna utan att slå Norge.
Okay. When Sweden is taking part in Olympic goal is not to win but to beat Norway.
Yes, this is what it is. But they are very good in Winter Olympics, so we can't make it, but we are trying.
Ah, very good, very good.
This is absolutely amazing, you know, and I was especially impressed that it picked up words like same-sex partnerships, which are very new to the language. The translator is good, but if they succeed with what's next, that'll be remarkable.
One of the exciting possibilities is combining the machine translation technology with the speech recognition technology. Now, both of these are statistical in nature. The machine translation relies on the statistics of mapping from one language to another, and similarly, speech recognition relies on the statistics of mapping from a sound form to the words. When we put them together, now we have the capability of having instant conversation between two people that don't speak a common language. That I can talk to you in my language, you hear me in your language, and you can answer back, and in real time, we can make that translation. We can get people together and allow them to speak.
The internet is just one of many technologies created to gather massive amounts of data. Scientists studying our Earth and our environment now use an incredible range of instruments to measure the processes of our planet. All around us are sensors continuously measuring temperature, water flow, and ocean currents. And high in orbit are satellites busy imaging cloud formations, forest growth, and snow cover. Scientists speak of instrumenting the Earth. And pointing up to the skies above are powerful new telescopes mapping the universe. What's happening in astronomy is typical of how profoundly this new torrent of data is transforming science. Astronomers are now addressing many enduring mysteries of the cosmos by applying statistical methods to all this new data.
The galaxy is a very big place and it's got billions of stars in it. And so to put together a coherent picture of the whole galaxy requires having an enormous amount of data. And before you could do a large sky survey with sensitive digital detectors that meant that you could map many, many stars all at once, it was very difficult to build up enough data on enough of the galaxy.
In the past, large surveys of the night sky had to be done by exposing thousands of large photographic plates. But these surveys could take 25 years or more to complete. Then, in the 1990s, came digital astronomy, and a huge increase in both the amount and the accessibility of data. The Sloan Sky Survey is the world's biggest yet, using a massive digital sensor mounted on the back of a custom-built telescope in New Mexico. It scanned the sky night after night for 8 years, building up a composite picture in unprecedented resolution.
The Sloan is some of the best, deepest survey data that we have in astronomy, both on our own galaxy and on galaxies further away from ours.
All the Sloan data is on the internet, and with it, astronomers have identified millions of hitherto unknown stars and galaxies. They also comb the database for statistical patterns which will prove, disprove, or even suggest new theories.
So we have this idea that galaxies grow. They become large galaxies like the one we live in, the Milky Way. Not all at once or not smoothly, but by continuously incorporating, basically cannibalizing smaller galaxies. They dissolve them and they become part of the bigger galaxy as it grows.
It's a startling idea, and in the Sloan data is the evidence to support it. Groups of stars that came from cannibalized galaxies stand out in the Sloan data as statistically different from other stars because they move at a different velocity. Each big spike on one of these distribution graphs means Professor Roccosi has found a group of stars all traveling in a different way to the rest. They are the telltale patterns she's looking for.
The evidence is accumulating that, in fact, this really is how galaxies grow, or an important way in which how galaxies grow. And so this is an important part of understanding how galaxies form, not only ours, but every galaxy.
The more data there is, the more discoveries can be made. And the technology is getting better all the time. The next big survey telescope starts its work in 2015.